Now I have the pleasure to present to Kevin Nutt from the University of Albany, and he will talk about quantity with uncertainty. He defines the physics of quantum mechanics and spacetime.
Right, great. Thank you for having me. Hello, everyone. And yes, I'm doing this. This work has been working on this with John Skilling from Ireland, and so we'll dive right in as long as everyone can see my screen here. So this work basically takes advantage of a slightly different perspective of what we are doing in physics. Instead of thinking about the natural laws, the laws of nature as being laws that are dictated by Mother Nature and that we all have to obey, I'm looking at this from a perspective of people wanting to quantify things, and we've gotten so used to quantifying things, and by that I mean assigning numbers to things, that we almost give it no additional thought. And of course, this is a very simple process. We learn to do this as children. We assign numbers for different properties of objects, and the larger things are typically assigned larger numbers. And of course, there's some arbitrariness here. There's some choice you can make. So here I have pictures of some batteries, 1.5 volt battery, a 6 volt battery, a 12 volt battery. And so we're assigning numbers to one aspect of this set of batteries. And classically, we tend to, because we're so familiar with this, we have come to think of these quantities as being properties of the objects themselves. So in fact, we even use them in the name. This is a 12 volt battery, and that's that number 12 is considered to be a property of the battery, which I think is that's a little too strong. And you can start to see where this is going to be problematic when we consider things like very small objects where the probes that we're using to study them are equally small. The assigned quantities in these cases really describe interactions rather than describing properties of the objects. So we often, our language often governs how we think, and how we think is described by our language. So these two things are coupled, and very often we'll hear people say, I myself will say things like, an electron has an energy E or has a momentum P, and that's really not a good way to think about it. The electron can't possess a momentum because the momentum of an electron is really observer dependent. You boost to another observer in a different frame, and they'll measure a different momentum for the object. They'll say, this electron has this momentum P. And of course, we know how these two numbers are related. But I think that one of the difficulties that we've faced conceptually is taking these numbers that we're assigning as descriptions of objects, descriptions of properties of objects, descriptions of the way that they're interacting with observers, and attributing them to being numbers describing properties of the objects. And that, I think that's really a wrong way of thinking, and it's caused us a good bit of trouble. The momentum and position and energy, these types of quantities really are describing the relationship between the electron and the observer. And so momentum is one description of the relationship. Position is a different description of that relationship. And the fact that the two descriptions are incommensurate really isn't surprising or unusual. They're just two different descriptions. And so there's been, in quantum mechanics, historically, there's been a lot of puzzlement over the fact that how can an electron not have a definite position and a definite momentum at any given time? Well, the fact is the electron doesn't have either. Those are descriptions of the relationship between the electron and the observer. And you can't have both of those descriptions can't hold at the same time. That's really what's going on there. It's really only mysterious if you think of these quantities as properties. So we've worked hard to give up these ideas of properties and thinking of this more in terms of description. So contextuality in this case becomes a little less mysterious. The context of the details of the interaction matter. And of course, how you are going to describe an interaction depends on the details of those interactions. And descriptions need not be commensurate. You can have complementarity. The electron doesn't simultaneously possess a momentum and a position. The electron doesn't possess either. That's a bad way of thinking. So what this does is it gives you a bit of freedom, which is interesting. And the profitability of such a perspective then is measured by what it allows you to do. And we've found that it allows you to actually do quite a bit. So if you're going to assign numbers to objects or properties of objects or interactions between objects and probes or observers, then you need to do so consistently. And the question becomes, how does one consistently assign quantities? So different operators may have different frequencies may have different symmetries. And these symmetries can be quite important because they will constrain the number of ways in which you can assign numbers to things. So let's say I have two sets of candy taffy here, and I'm using candy because what I'm going to be doing with these taffy is rather simple. You've all known about this since you were kids. So I've got a set here A of some taffy, and I've got a set B of some taffy, and I'm going to combine the two. So let's say I have set A in one hand and set B in the other hand, and I'm going to put them together. Now, if I want to quantify these sets, basically assign numbers to the sets of taffy, one obvious way to do this that you're very familiar with is to count them. We'll assign a number describing the cardinality of the set. And one can then ask the question, well, how do you take the number that you assign to set A and the number that you assign to set B, and how do you combine those numbers to arrive at a consistent number that you're going to assign for set A with B? Of course, you all know the answer to this already. You add them. And my interest in this question came from the deeper question that I had in graduate school, which was, why do you add them? I know that it works. It's obvious that it works. I've been doing this since I was a kid. But why is that the case? Can you prove that it has to be that way? And indeed you can. There's several different properties that this with operator, basically combining stuff in two hands, exhibits. This combination property with exhibits closure in this case. So if I take stuff A and combine it with stuff B, the stuff that I have in A with B are the same kinds of stuff. If I take taffy in my left hand and taffy in my right hand and combine them, then I still have a bunch of taffy. So that's closure. Another symmetry that you have with this operator is commutativity. Doesn't matter which hand I have the set A of taffy in, which hand I use to pick up the sets in the first place. I could switch hands and I still have the same result when I combine them. That's a symmetry. If I have 3 piles of taffy and I start picking them up, I can pick them up in various ways, and the result is equivalent. That's called associativity. And the idea is that the width operator is such that I can keep grabbing piles of taffy if I want. And so mathematically, I ought to be able to keep combining them. So these are the 4 conditions that the width operator has to satisfy. And you can prove, this is a theorem, you can prove that if the width operator satisfies these 4 conditions, and you can think of associative commutativity as just shuffling. I can shuffle up the piles and I get the same result. Then you can show that if you're going to quantify the set A with a number represented with lowercase a, and you're going to quantify the set B with a number given by lowercase b, then A with B is basically going to have to be quantified by something that's isomorphic to A plus B. And that's a theorem, and that's something you can prove. So you might say, great, that's something we've known this all along. Not very exciting. I've known this since I was 3 years old. But it turns out it's rather profound. And so here's the example. If I assign the number A, 3 to the set A, I assign 10 to set B. There's a little taffy hiding under this one. So now when I combine them, the number that I assigned to the set A with B is given by 3 plus 10, or 13. And that will give me a consistent means of quantifying these objects. So how well does this work in general? Well, it works pretty well in general. We use it all the time. We count all sorts of things, from taffy and rocks to gallons of gasoline to cars on the highway to stars in the sky. But let me give you an example where it doesn't quite work, because one might be led by, because of the generality of the application of the mathematics, you may be led to thinking that this is some kind of universal physical law. And it's not quite that simple. This is a description. I can emphasize the fact that it's a description by showing that it is observer dependent. So here's another example. I have 2 sets of objects. Each of these sets contains molecules. In the ones on the left, I have 2 butane molecules. And in the set on the right, I have 13 oxygen molecules. There, maybe this is in the way on my screen. So now I'm going to combine the 2. So on the left, I have 2 molecules. So I could assign, you can conceive of assigning this a number 2. On the right, I have 13 molecules. I give it the number 13, and I'm going to combine them. And you expect to have 15 molecules, which is nice. And that works as long as you don't shake this up and make it too hot. Once you make it too hot, this happens. And you no longer have 15, you have 18. And you have 18 carbon dioxide molecules and water molecules both. So what went wrong with our little rule of additivity? In this case, 2, it should be 2 plus, I have the numbers up here wrong, but our 2 plus 13 actually gives me 18. So why did that happen? What went wrong? The answer is quite simple. What went wrong is we violated one of the conditions for the width operator. The width operator lacks closure. You don't have the same kind of stuff at the end that you had in the beginning. So whether addition worked or not depended on our description. If I were to go back here to the beginning, and instead of counting out molecules, if I counted how many atoms I had, And here I have 4 times 2, which is 8, and then 10. And so that's 20. So I got 28 atoms on the left, and I have 26 atoms on the right. And now I throw them together and shake up the box. I still have the same number of atoms. You can add the number of atoms and you get the right result. So addition works if you count the atoms, but it doesn't work if you count the molecules. So that shows that there is a dependence on the level of description that you choose. So whether additivity works depends on the description you chose. And the laws of nature shouldn't depend on description if they're going to be some universal law. So this isn't about a law of nature. This is about describing things with numbers. So there, of course, there are other operations you can do. You can take 3 copies of the set A, and I'll call that 3 of A. So this is a new operator called of. I can replicate things, and it turns out this of operator is obeys associativity, and the of operator is distributes across the with operator. So you have distributivity. So here we have associativity and distributivity, and you can prove, again, similar to the proof before, the associativity means that the number that I assign to, so if I assign a number to, if I have this number A and I assign a number to B, little a and little b, then the number that I assign to A of B is going to have to be, it's going to be some function of little a and little b. And associativity forces that to be isomorphic to addition. But because we used addition for the with operator, the fact that we have distributivity forces that isomorphism to settle on one particular transform, which is basically multiplication. So multiplication is isomorphic to addition, so it satisfies the associativity, and the multiplication will satisfy distributivity. So this is a theorem, and so the idea is you multiply the numbers together. So now when I take 3 of A, if I assign a number 3 to A, kind of unfortunate I use 3 here, basically when I'm done, 3 of A is going to give me 3 times 3 or 9 pieces of taffy. And you can prove that this has to be the case because of associativity and distributivity. So these are rules for consistently quantifying numbers, or quantifying things with numbers. And now we're going to push this to an extreme. We're going to consider the case that we encounter in quantum mechanics, where we are studying very small objects with very small objects. There's a point where we get to where we are studying objects for which there are no smaller probes by which we can use to study these, and we may obtain some number x in a measurement, and which we would use to quantify this interaction, but we have to acknowledge that we're going to have some uncertainty as to the value of this assigned quantity x. You can also think of it this way: we have some quantity describing the system, some describing the probe. So you put the two together, you really need 2 numbers to describe the interaction between the system and the probe. Now this uncertainty, the relationship may be more intimate than the usual x plus or minus sigma uncertainty that we're used to from dealing with Gaussian probabilities and probability theory. And in fact, I would like to, in this case, if I did want to quantify things this way, I would have to derive this plus or minus as being a function relating these two. So to back up and work to do something like that, we're going to not assume that this is the case. Instead, we're going to assign 2 numbers here. One number is related to a number quantifying the interaction x, and another is going to x1, say, and the other is going to be x2, which will quantify uncertainty. We just have 2 numbers here instead of 1. So what happens when we consider similar operations like the with operator and the of operator, and we start combining things, and we are using two numbers to describe these interactions rather than just one? So we'll look at associative commutativity again, which previously with scalars and the Taffy gave us a sum rule. We find that that's the case here as well. So if we have some set A, something A that's described by two numbers x1 and x2, and then we have a B described by two numbers y1 and y2, then A with B, where this with operator is any operator that exhibits closure, associative commutativity, and reproducibility, then A with B has to be represented up to isomorphism by component-wise summation. So we would then assign for A with B, we would assign numbers x1 plus y1 as one number and x2 plus y2 as the second number. That's not so unusual because it's not so different than you can see the scalar case right there. Things get a little more interesting when you consider an additional operation like the of operator, where you have associative distributivity as well. So here, upon interaction, associative distributivity, which we'll use this operator as dot, is we're trying to figure out what dot would be. We will have distributivity here. We also have associativity, and we also have that we have component-wise summation for the plus here, and that requires that this dot operation has to be bilinear. So whatever numbers x and y you have in the original pairs, the result is when you combine them has got to be some linear bilinear combination of these objects, where these gammas here are coefficients that we have to identify. So these basic symmetries are common in the systems that we work with, and that is why we use addition all of the time, because we have associative commutativity holds often, so addition works. And in physics, generally we have associative commutativity and associative distributivity, and that is why physics is fundamentally linear. Excuse me. So now, whereas scalar quantification resulted in one multiplication rule, the pairwise quantification, where we're carrying with us a number quantifying some uncertainty, results in 3 multiplication rules, which is interesting. So, and that these come about from looking and seeing what gammas are possible. So it turns out that there are 3 sets of gammas that are possible, and all the different versions reduce to 3 different types of operations. One of these here, you'll see the first one, A, looks like complex multiplication. So you're basically treating these as complex numbers. And B is similar, but we have addition here, and C is also similar, but not the same. We can rewrite this as as a matrix operation, where A looks like this, B looks like that, and then we operate on the vector y1, y2. So these are the 3 different multiplicative operators that we have, and we will see that much of physics comes from these 3 operators. So without loss of generality, we set the determinant of these operators to 1, and we do that so that repeated application doesn't diverge to infinity or collapse to 0. That would be pointless. And that means that there's really only one free parameter related to the ratio of x2 to x1, which gives us 3 possibilities. We have something like a rotation matrix for multiplication rule A, we have something like a hyperbolic rotation for multiplication rule B, and we have this other matrix for operation C. Each of these three will obey those symmetries, so they may be useful in quantifying things in the real world that obey those symmetries, or interactions in the real world that obey those symmetries. So of course, we can write these operators in terms of infinitesimal generators. This is what the generators look like. And we then see that generator A is basically rotation by some phase angle, and which is what I had originally said. So there's a rotation matrix. So generator A basically rotates by a phase angle. And the sum and product rules in these cases are those of complex arithmetic, and the pairs are complex numbers. Unit quantities identified with unit modulus determinant, which is modulus squared. And we find that the inherent uncertainty in a unit object refers to what remains unidentified in X, which is namely the phase, this rotation, so that every time we have an interaction, each new object you interact with brings with it an unknown phase. So now we have to rely on probability to deal with this inherent uncertainty properly. Our ignorance of phase is uniformly distributed, so we can assign a prior probability to the phase 1/2 pi. And to obtain a likelihood of a given outcome, which is what we're computing when we do quantum mechanics, we must marginalize over all of the unknown parameters, which are all of the unknown phases in the interactions. And if we perform this marginalization, you see that we are basically summing modulus squared quantities. And this is really why quantum mechanics is a probabilistic theory. And the likelihood is additive because of the scalar sum rule, and it depends on the modulus squared, which is the Born rule. So you can show that all of these things arise from these simple symmetries. So here you can see, here it looks like the foundation of quantum theory is pretty elementary and simple. Quantity and uncertainty fuse together into complex numbers, with uncertainty really referring to phase. And the observable quantity is the modulus squared, which is the Born rule for arbitrary amount. And that represents ensemble averages, which is what the experimenter measures. So we have that. What's nice about this is quantum mechanics and probability theory are derived from the same symmetries. They can't possibly contradict one another for that reason. And in physics, we make predictions which are quantified probabilistically in terms of likelihoods. And so given those likelihoods, Bayesian analysis then computes posterior probabilities, which assess the models in light of the outcomes that are actually observed. And that is the relationship between quantum mechanics and Bayesian inference. Quantum mechanics deals with computing likelihoods, and likelihoods are used in performing inference. So now we can go a bit further and see how the multiplication rule B comes into play. These three different rules are potentially going to be used to describe different types of interactions. And so rule A, multiplication rule A we see is used in quantum mechanics. What is B good for? Well, B, because these are all possible descriptions, we can then ask what could we possibly describe with B or C? They're going to be consistent with the symmetry, so they would be good descriptions of something. And I'll look into that briefly here. So here we can consider objects that can exist in two states, let's say up and down. This gives us a quantification consisting of a pair of complex numbers. basically using the rules A, the multiplication rule A, and we'll have pairs of complex numbers now. And qubits, we'll call these qubits, will obey associative distributivity. So the representation is two-dimensional over the complex field. And these generators, these generators that we have will give us the Pauli matrices. So B, the generator for multiplication rule B, gives you sigma x. I times the generator for multiplication rule A gives you sigma y, and then together B times A gives you sigma z. So these are the Pauli matrices. And so the multiplication rules A and B together give you the concept of spin. And we see that we get the scalar quantifications come from these different, these three Pauli matrices. And this gives us a relationship between these new quantifications that we can construct from these operators. And this is really the first clue that 3+1 spacetime emerges from quantum mechanics. So with complex coefficients, these generators define the 6-parameter Lorentz group, under which ensemble averages of independent samples results in this relationship, which is invariant, or this quantity, which is invariant. So if I go back to those original multiplication rules, these two here together basically give us a 6-parameter Lorentz group. So we can see that when you think of these multiplication rules as being constraints that constrain your description of things, you can see that the descriptions we use in physics are actually coming from these constraints, and they ought to be. It gives you the possibility of deriving physics, which is quite interesting. One could have potentially derived physics before encountering the physical world, which is quite a thought when you imagine that the physical laws are somehow laws dictated by Mother Nature. If you think of the physical laws as being constraint equations that constrain any attempts at quantifying physical things, then it's not so surprising. So the shift in perspective on what you mean by a physical law gives you a great deal of freedom. So we now have these symmetries of associativity, commutativity, and associative distributivity, along with the consideration of uncertainty, give us the basic mathematical descriptions of the universe. We get from this, you can get the quantum mechanics as a probabilistic theory. The Pauli matrices and spin derive from multiplication rules A and B. This also gives you concepts of energy and momentum and phase and action. And from that, you can then integrate using rule C, which I don't have a slide for. I should have made that. I didn't want this to take too long. And you can see that operator C is an integrator. I'll go back to that. Here we go. So here's operator C. If you imagine multiplying it times something like dt on the top and then t0 down below, you can see that this is going to basically integrate phase. So time, it comes about from integrating phase. And this basically allows you to integrate time, which then when combined with the other two, allow you to integrate, you can integrate phase up to obtain time, and you can integrate momentum in the other two up to obtaining positions. So it works backwards from what we're used to. What we're used to is we start out with wave functions and we have positions and times, and we take derivatives to obtain energy and momentum, which are supposedly more fundamental. So we basically work backwards in in the traditional way. We start out with something higher level, position and momentum, or position and time, and we take derivatives to get momentum and energy. This is actually going from the ground up, which is what I think would be a better foundation. That's how you build things, from the bottom up. So here, basically, we have energy and momentum and phase coming in from the beginning. And then with operator C, you can then integrate that to getting a three-dimensional space-time. And that comes out as an integral of phase and energy and momentum. So this is the direction our work has taken. And and why does mathematics work? Which is a question that's always had me wonder. Here it's easy to see the symmetries. These symmetries constrain our mathematical description of physics, which is why it works. And that's why it's derivable, which is interesting. Universes can't just do anything. As long as you have these symmetries hold, then your description of systems or interactions that obey these symmetries are going to have to follow these mathematics. And that basically is the theorem. So here's one of our most recent papers on this. So I hope you enjoy that, and thank you.
Okay, thank you very much, Kevin, for this nice talk. The people who want to make a question or a comment can indicate it in the chat. I have a little question.
Yeah.
Do you think that this analysis can be replicated in another physical theories that use another type of space or space-times, like string theory or this kind of things?
Oh, I didn't quite follow that. I'm sorry. The connection wasn't so good for me.
Sorry.
Sorry.
Do you think that this analysis can be replicated in another theories that use another kind of space-times, like in the string theories or this kind of?
No, that's a good question. And that's basically where we're headed with this, is we want to see it from what we have so far. It looks like these symmetries allow you to generate space-time as integrals of quantity, more fundamental quantities like phase and energy and momentum. And so we want to look into that to see if you can build space-time up from that foundation. And if you build space-time that way, if you can do that, then it's going to automatically be consistent with quantum theory. So we would have a theory of space-time that's consistent with quantum mechanics from the get-go, which is really how you would want it.
There is a question from Federico Holly.
Hi, Kevin. Thanks for this
Federico.
from this talk. Yeah, it's great. So I wanted to know what's your take on photons, because you mentioned that when you count atoms and molecules, well, that the counting, it depends on the level of description that you are taking, right? But then if I have a laser, an attenuated laser, and you prepare a coherent state, then you will have a superposition of different numbers of photons. So you don't have a definite particle number. So what would be your take in that situation? How many photons do I have? Or photons in that case will not be real entities and only the quantum field? What will be your take?
Well, that's a really good question. That's something I hadn't considered. If additivity doesn't work, then you've violated one of those four conditions, and that would be my first guess. And then then the question would be, which of the conditions are violated in that situation? So in the case where I combine butane molecules with oxygen molecules, the condition that's violated is that of closure. So it's hard to imagine that you're going to have a problem with closure when combining photons. So yes, I'm curious about this. I'll have to think about that. Thank you.
Thanks.
That's a very good question.
Thanks.
Okay, we are in time, so thank you, Kevin, again.
Okay, thank you so much.
We will pass to the next question, to the next talk. Eloisa, are you here?
Yes, hello. I will share my screen.
This talk
Are you?
is in charge of Eloisa Cuestas from the National University of Córdoba.
Can you see my screen now?
Yes.
Okay. So thank you very much for this opportunity to share our work. And also my internet connection is not very stable, so if we experience some troubles, maybe I will have to turn off my camera. So this is the outline of the talk. First, I would like to briefly introduce our group and our approach, which is known as composite boson or boson formalism. Then I would like to mention in a few words our research lines. And after that, we are going to speak about our last work, in which we focus on strongly bound fermion pairs on a ring. And we will finish with a summary and some comments. So when finishing the talk, I would like you to have a mental picture on how do we work and what topics do we work on, and why do we choose to work on these topics and with this particular approach. So I am in a kind of new group at the National University of Córdoba in Argentina. My postdoc advisor here is Ana Magtei. She comes from the quantum information area. And we collaborate with Alex Bubri from Spain, who comes more from the atomic and molecular physics area and field body physics like me. We also collaborate with Cecilia Cormick, who has a lot of experience in ultra-cold atoms. And the work I'm going to speak about is our last work with Ceci. So we come from different research areas, but we share the theoretical approach, which we complement with simulations, with numerical simulations. And as I said before, we work with something called the composite boson or coboson ansatz. This ansatz was introduced in 2001 by Anthony Leggett for bosons and Monique Bascott for fermions. Here are some references. And the ansatz propose an expression for the ground state of a system with certain properties that we will see in short. And the basic idea of this ansatz is to treat a composite particle such as an atom or nuclear molecule as if they were ideal bosons. The simple case could be to think in two bosonic or fermionic particles, making a new composite entity that behaves like an elemental boson. This strategy to deal with composite particles is a widely used strategy in many body physics, and it is justified a posteriori because it works in the sense that it allows us to predict and manipulate the behavior of physical systems. When we think in fermionic particles, the underlying idea is that if we exchange two fermionic particles, the total wave function must be antisymmetric under this exchange. But if we exchange two fermions, the total wave function must be symmetric, like in the case of bosons. Then we can think in two fermionic particles like a new bosonic entity. Of course, when we use the formalism with fermions, we must take into account the Pauli exclusion principle. We interpret that one of the main goals of Monique Scott, the creator of the co-boson ansatz for fermions, is to show that even in the presence of strong fermionic correlations, the co-boson ansatz captures the physics of the system. In this context, one of our main goals as a group is to test the ansatz, and that's why we are always looking for concrete applications in experimentally achievable system to contrast the results obtained using the ansatz with actual or real measurements. And one example of such systems are the ultra-cold Fermi gases. And also, as I said before, our group members come from different areas, and one of those areas is the quantum information, and that's why we are very interested in the role of entanglement on the ideal bosonic behavior of composite particles. So we can then we can formulate like two questions or two main questions that guide our work. First, a very fundamental question, which is under which conditions a pair of fermions can be treated as an elementary bosons. Some authors have explored this question and point out that the key to understand the origin of composite behavior relies on entanglement. And the second question is related to the extent of the ansatz in particular and the formalism in general. And this is when can we use it and when we can't. And the results I will show in the next slides are more related to this second question. But before going to those results, I would like to briefly review the co-boson approach as formulated by this author, Law. The main idea of the co-boson ansatz is then to build the unpolarized state of an even number of particles of two different species upon the single pair state ground state, which is therefore a two-body or two-particle state. For us, these two particles must be distinguishable, meaning that we have two different kinds of particles, A and B, or red and blue. And that could be, for instance, electron of different spins or atoms in different hyperfine states. But the whole system must be unpolarized. We must have the same amount of red particles and blue particles. So in the description proposed by Law, the pairing structure is explicitly used, and the observables are obtained in terms of the a single particle state, and that, in my opinion, makes the results more intuitive or imaginable. Giving a kind of co-bosonic recipe, first we need to find a good two-particle or single pair state, and with good I mean to look for a state in which the interparticle interactions are taken into account in the best way as possible. And after that, we need to find a decomposition of the state reflecting the pairing structure between the two types of particles in terms of the single particle state. This is the Schmidt decomposition of the state. So if we have red particle in a given single particle state labeled with J, then we have a blue particle in the J state, but of the blue particles. Then, based on that decomposition of the single pair state, we define the co-boson creation operator here that creates a pair of these two different particles like a new entity, having into account that when we create the particles and we fill up the single particle state, we must obey the Pauli exclusion principle. The state of n of such pairs come from successive pair creations from the vacuum. This B here is the vacuum, and requires a normalization constant. This normalization constant has the information about the exchange correlations between particles of the same species among the different pairs of cobosons. That will be this red one with this other red one, between, for example, this blue one with this other blue one here. So this sum here is performed over different states in order to fulfill the Pauli exclusion principle. And it turns out that when the ratio between this normalization constant here goes to 1, the cobosons behave like ideal independent non-interacting bosons. While a ratio near or close to 0 reveals strong deviation of the ideal bosonic behavior, meaning that the fermionic character of the constituents of the red and blue particles is important. So when using the coboson ansatz, the many particle physics arises from the state of a single pair and from the fermionic exchange correlations. This means that the interparticle interactions beyond the exchange interactions are only being considered in that initial two-body model for the first pair, for a single pair. And that's why it is so important for us to have a very good model for the first single pair. As I said before, there is a connection between entanglement and the ideal bosonic behavior. And in a few words, Leo pointed out that the composite particles can be treated as bosons when the red and blue particles are sufficiently entangled. And this is equivalent to two things. First, the effective number of available single particle states must be large compared to the total number of composite particles. And second, the available physical space for each pair must be large than the pair of each one, than the size of each one of the pairs. In other words, we need to have enough single particle state to accommodate all the particles, and we also need to have enough physical space to host all the pairs. And we can think on this like an egg saver, and the cobosons would be the the eggs, and the states will be the places in the egg saver. So if we have at most 12 eggs, then we can accommodate them all and we will be okay. But if we have more than 12 eggs, we will have a problem. Also, everything will work with chicken eggs, but if we have a big crocodile egg, this is not going to work. So what this entanglement-related hypothesis says is that if the red and blue particles are sufficiently entangled, then we have a good egg saver for the egg type and also the number of eggs we are dealing with. So we can accommodate or put our cobosons in the state space and also in the actual physical space. As a personal comment, this understanding or addressing composition from many areas or many point of view is what I like the most about the formalism and what keeps me always motivated. I also said that in order to test the ansatz, we are always looking for concrete applications on experimentally observed system depicting strong fermionic correlations, and also systems that were widely studied with other theoretical approach, like exact diagonalization of the Hamiltonian or quantum field theory or quantum Monte Carlo simulations, among others. For example, in 3 dimensions, we study ultra-cold Fermi gases, and in 1 dimension, we study Wigner molecules, the fermionization of distinguishable fermions, and also fermions in a ring. Okay, now we almost reached our last work with Ceci. So the Gaussian ansatz is expected to work or to be valid for short-range interactions, for dilute systems, and also highly entangled constituents. But it turns out that in this work here, part of our group studied strongly bound composite bosons in a discrete lattice and show that the ansatz fails in this one-dimensional model. And the ansatz fails because it is not able to capture the long-range correlations in the system. In a two-dimensional lattice, the ansatz works, and Anna and Ceci check that the fidelity between the cobosonic ground state and the true or the correct ground state increases when the two-dimensional system becomes more and more dilute. Then one of the main conclusions of this work is that the dimensionality plays a crucial role. But we still wonder what happens with a continuous system. And that leads us to focus on the case of two fermion pairs on a ring of length L, where the red and blue particles interact with a delta attractive potential. The correct or true ground state for this system is well known. It is solvable by means of the Bethe ansatz, and the ground state for the unpolarized case can be found in this paper, this reference here. So we wanted to compare this known energy with the cobosonic energy. And to do that, we follow this procedure, which is different from the one I told you before. So first we solve the two-body state as or single pair state as before. Then we build the creation operator for a single pair, and then we build the two coboson bases, and at this point we reach the two pair or four particle part. And having that basis, we then calculate the overlap and Hamiltonian matrices, and with those matrices we find the ground state. And then having the ground state, we could calculate the fidelity between the true ground state and the one given by the ansatz. And we also calculate the conditional probability of finding a particle of a red particle in a given position when another red particle was found at zero position. To solve the two-body state, we rewrite the Hamiltonian in the center of mass and the relative coordinates. And when doing that, the Hamiltonian decouples, and the wave function is a product between the center of mass state and the relative states. And as we can see here, the solution of the center of mass equation are the free particle states. The relative states can also be obtained, and it turns out that when the interaction increases, so the system becomes more and more attractive, the relative ground states becomes more and more localized. That will be going from this black curve here to the blue one. And for a strong attractive interaction, we can approximate the relative state with this simple expression here. And in this plot, we can see the fidelity between the complete ground state and this approximation here. And it goes to 1 for strong attraction, meaning that this is this expression is a good approximation for the complete two-body states. We could also obtain the exact Schmidt decomposition of these two bodies ground state. And with the Schmidt decomposition, we were able to corroborate that this state fulfills all the criteria for good bosonic behavior proposed so far. Of course, the criteria that we, to the best of our knowledge, the criteria that have been proposed so far to the best of our knowledge. In this plot, we can see that the two particles are highly entangled in the when the attraction becomes more and more attractive, the linear entropy goes to its maximum value. And we also corroborate that the system fulfills some criteria for good bosonic behavior based on physical ideas, as this one here for each one of the Schmidt coefficients, these coefficients here, which comes from the notion that at low density prevents the overlap between the wave function of the fermionic parts, and therefore their fermionic character will not be important. Once we have the two-particle state, we build the creation operator for a pair like this one, where this operator here creates a red fermion at position X. And having the creation operator, we build the two coboson bases here. And because of the symmetry of the problem, and since we are looking for the ground state, we can restrict us to the space with zero pseudo-momentum, so that the ground state will have this form here, where this Km is a cutoff, while the cobosonic state will have this this other form like here, that will be all when all the coefficients in this expression are zero, except for the first one. And once we have the two coboson bases, we need to calculate the overlap matrix, because the basis is not orthogonal. And in this step, we must use the commutation and anti-commutation relations for the creation operators, and then we must perform the resulting integrals. And the complete expression for the overlap matrix is this one. And the important thing here is that for a very strong attraction, we can expand this expression on this small parameter to obtain this other quite simple expression. And we can also compute the expression for the Hamiltonian, and we can also expand it on the same small parameter as before. And now we are left to find the ground state. So we need to solve this generalized eigenvalue system. And with the complete matrix elements, we can solve this numerically. And with the Taylor expansions, we can obtain some exact results. But before going to those results, we are ready to compute the cobosonic estimation for the energy of the four-particle ground state, which is this one here. And we can see that the coboson ansatz is not giving us the correct four-particle ground state, because the true energy will be obtained if we put here a 2, because n is the number of pairs, and we can see that this is a very large correction to the energy of two non-interacting pairs, and here we don't have such a very large correction. And even though the ansatz failed with the Taylor expansion of the Hamiltonian and also the overlap elements, we could reobtain the exact correction for the ground state energy. this one here, and we also could obtain the exact coefficients here. And then with those coefficients, we could calculate the exact fidelity between the correct state and the cosonic state, and we obtain this number here. This fidelity is not quite good, but it is in agreement with the previous results in the one-dimensional lattice model. So the results are consistent with the previous works in one dimension. And finally, we calculated the conditional probability. Here, we obtained this expression here, and it differs from the cobosonic correlations. In this plot, we can see that the correct probability, which is this red one, is quite smooth, and the cobosonic one, which is this gray one, is quite flat with an abrupt decay around 0. In 0, both probabilities must be 0 because the fermions of the different species cannot be at the same position. This flat probability is in agreement with the previous results in the lattice work. So the main conclusions are first, that the ansatz does not give a good approximation for the ground state, because it doesn't capture the spatial correlation between the pairs. And second, that even though the ansatz fails, we could show how the coboson theory, or using the complete formalism, we can recover the correct ground state. Then we see our work as a warning sign against the light use of the coboson ansatz, especially in the description of one-dimensional problems. Beyond this particular case, and as a global conclusion, I will say that the coboson formalism is a powerful toolbox to address few and also many body systems. It is also useful to address entanglement in many particle systems. And the ansatz or the coboson formalism also allows to study a wide variety of systems. The particles can be fermionic or bosonic, distinguishable or indistinguishable. And the ansatz has evolved towards a framework merging atomic and molecular and quantum information and many body physics. And this is quite interesting, at least for me. And the main point I would like to stress in the context of this conference is that most of the proposed criteria for good bosonic behavior until now are related to entanglement, and even so, a proper criterion for good bosonic behavior is still elusive. The system, for example, fulfills all the entanglement criteria, as well as some other criteria based on physical ideas, and even so, the ansatz fails. So there is a fundamental underlying question, which is what is the role of entanglement when addressing composition? And this question is open. So thank you very much. And here are our emails and a photo of all the people that had been involved in the group. And also Martin is doing his PhD with Anna, and he will be presenting a poster on Friday about some related things. So you can see Martin's post.
Okay, thank you, Eloisa, for your talk. If there is a question or comment, you can indicate the chat, and we will give you the word.
Fede.
A question from Federico Pauli.
Hi, Eloisa. Thanks for this talk. I'm still trying to understand the physics of this. It's really complicated for me, because you mentioned that entanglement. I mean, in the situations in which the coboson ansatz works, entanglement plays a key role. So when you have high entanglement, it works. But I wonder what happens in an atom. Suppose that you have an atom. But in an atom, if you have the right numbers of electrons and protons and neutrons, it will behave like a boson, right? But this atom could be in a thermical bath with no entanglement at all. So why an atom behaves like a boson?
Well,
that I don't understand. I mean, I understand the idea, but it's so.
Well,
can you say something about that?
Actually, in the paper, in the paper of Tsutsiki, one of the PRL I show on the slides, they give us an example, the hydrogen atom. And they said that we have two fermions, two distinguishable fermions, an electron and a proton, and they calculate the entanglement between the electron and the proton, and it is quite high. So that will be an explanation of why the hydrogen atom behaves as a boson.
But how can it be so high? It's puzzling, you know, because I imagine an atom.
Because of the interaction.
Yeah. Oh, yeah. But also an atom is interacting with the electromagnetic fields, right? And it can be emitting or interacting with other atoms, like in a thermal bath. So it's really puzzling for me. Does it mean that? Yeah.
Yes, you could think, for example, that when you have those other interactions, somehow those interactions interfere between, for example, the interaction between the electron and the proton, and then the atom like loses the bosonic behavior somehow.
Okay,
yeah,
so you say
I would think something like that.
You say that perhaps if I have the atoms isolated and few of them, and depending on the interactions, they will behave like bosons. But if I mess up with that situation and I put, I don't know, put them in a cavity with radiation and everything, they might lose the boson behavior. Great. Thanks, Eloisa.
Yeah.
I think it's, okay, thanks.
Yeah, I will say that. Okay.
Okay. Question or comment? No. We are in time to make a coffee break. So we stop here and we will return in 15 minutes.
I think Olympia has a question, but I don't know. Or she has a raised hand. Maybe it's all
It's an applause.
Okay. Okay. Okay.
Great.
Okay, thank you.
Thank you, Eloisa. And we will back in 15 minutes. Pauli?
Right? Can we try to?
Hello, Rodolfo.
Yes.
Okay. We'll try to
Share the screen.
wait a minute because Federico have to stop to share. Now, now you can share.
Hello, Rodolfo.
Hello.
Hola Rodolfo, tanto tiempo.
Hola, ¿cómo están?
Hola.
I don't find. No encuentro mi.
Igual, todavía queda un poco de tiempo.
No sé si lo ven.
Ahora estamos viendo una página de Zoom.
¿No están viendo un PDF?
No.
No.
Ahí, trato de vuelta con el share. Ahora.
No, a ver, empecemos de nuevo. A ver ahora y hay que cuando ponga compartir pantalla le aparecen varias opciones. Hay que seleccionar y que quede en azul la presentación.
I have selected the PDF file. I'm including full screen mode.
It's
No,
sharing, but now I see a black screen. I don't know why.
What kind of screen?
Black. It's only black.
Only black?
Yes.
Well, in my screen, I see that Rodolfo is starting to share, but I see nothing. It's just, yeah, like a sort of announcement. Perhaps when you find the choice of sharing screen, you can share the whole screen or something like that.
I will reconnect my Zoom.
Se le desconectó. Ahí lo presionó.
Listo.
Now I press share screen.
Sí, ahora sí.
Perfecto.
Okay, we are in time. Our next speaker is Rodolfo Gambini from Uruguay, from the University of La República.
Okay. It is a pleasure to participate in this conference about quantum foundations. I will talk today about an approach to the measurement problem based on a quantum gravitational notion of time. I will start with an outline of the talk. I will present the orthodox view of the measurement problem. I will analyze the role of time in general covariant theories and quantum mechanics. I will present a description of the evolution of quantum systems using a quantum notion of time. I will discuss quantum gravitational limits on the precision of physical clocks. I will recall the environmental decoherence program in the measurement problem. And I will propose a solution of measurement problems using physical clocks. I will finish with some philosophical considerations. Well, the problem of measurements in quantum mechanics arise in standard treatments as the requirement of a reduction process when a measurement takes place. Such process is not contained within the unitary evolution of the quantum theory, but it has to be postulated externally, and it is not unitary. Reduction is usually justified through the coherence due to the interaction of a large measuring device with an environment with many degrees of freedom. Objections have been raised onto two aspects of the solution of the problem of measurement through the coherence. In first place, since the evolution of the system plus environment is unitary, the coherence persists when the environment is included, and it could potentially be observed or regained by observing the environment. And the second criticism has to do with the fact that in a picture where evolution is unitary, nothing ever occurs. This is the Bell-Or problem. The final reduced density matrix of the system plus the measurement device will describe a set of coexistent options and not of alternative options with definite probabilities. We shall discuss, in first place, the issue of time in general covariant systems and propose a solution for this issue. The problem of time in totally constrained systems like general relativity is the following. The system is completely described by a set of constraints. In the case of general relativity, the constraints are part of the Einstein equations, and the other equations are consistency conditions. And the constraints satisfy first class, that is, the Poisson brackets of two constraints weakly vanishes, that is, vanishes on the constraint surface. The generator of the evolution also generates gauge transformations because the Hamiltonian may be written as a linear combination of the constraints.
Rodolfo,
Yes.
no estamos viendo nada más que la primera slide. ¿Está bien eso? O...
No. Estoy mostrando. I'm showing the second one.
We can only see the first one.
Now,
No.
Quizás se deja de compartir y vuelve a compartir, pero cuando comparta, compartir el escritorio, o sea, toda la pantalla, no solo las slides. Quizás ahí te va a dejar. Ok, ahora
Sí, ahora sí.
que mueva, a ver.
A ver.
Perfecto.
Ya sí, ahora sí.
okay. Then I continue with the same slide. I was talking about the general covariant systems. General covariant systems are such that the Hamiltonian is a linear combination of the constraints. And in the case of general relativity, constraints are first class, and weakly, the Poisson bracket weakly vanishes. Observables are gauge invariant quantities, and therefore the Poisson bracket with the constraint vanishes. And as the Hamiltonian is a linear combination of the constraint, the observables commute with the Hamiltonian. And therefore they are constant of the motion. Only Dirac observables can be quantized in the space where the constraints are fulfilled, called the physical space. We live in a generally covariant universe where all the observable magnitudes are constant. Then we have the issue of time. If the physically relevant quantities in totally constrained systems as general relativity are constant for the motion, how can we describe the evolution? There are several proposals for the description of the evolution. The first one is well known, is the gauge fixing. One introduces a classical parameter that plays the role of time, that I'm calling the parameter tau. And one assumes that certain function in the kinematical space is equal to this parameter. For instance, for a free particle, the Q naught is equal to tau, and quantize the gauge fixed theory. In this case, where the time will be a classical variable, and you quantize after choosing the time. There is a second proposal known as the evolving observables that was proposed by Barman, DeWitt, and Robelli, among others, and consists in the following. You consider a one parameter family of observables, that is of quantities that have vanishing Poisson bracket with the constraint. And these observables are such that when one of the variables of the system, in this case Q1, takes the value of the parameter, then this observable takes the value of another kinematical variable of the space. Let me discuss an example. For instance, for the relativistic particle, you have here the constraint. You have two Dirac observables, the momentum and the position, the initial position of the system. And you may define an evolving observable that is this quantity that depends on T. Notice that when T is equal to Q naught, then this term cancels with this, and you recover the position at this time. But one needs to assume that there are variables as Q naught that are physically observable, even though they are not Dirac observables. To know when the measurement is carried out, we need to observe a case-dependent quantity. And this is a problem in this approach. There is a third proposal that consists in considering conditional probabilities. The idea is that one promotes all variables to quantum operators and computes conditional probabilities among them. For totally constrained systems, this approach also runs into problems. Which variables to promote as a clock? Dirac observables are of no use because they are constant. Page and Wouters propose using kinematical variables. And recently, Henning, Schmidt, and Locke have shown that it is possible to use kinematical variables in a consistent way. But again, you are using quantities that are not observable in the physical space. In any of these approaches, one encounters the same problem. The evolution can only be described in terms of an ideal, essentially classical time. This is the type of time used in the Schrödinger equation. There is a solution to this problem that allows to use physical clocks, that is, clocks that obey the laws of quantum mechanics and general relativity, like the ones in our universe. We will elaborate on that and propose a solution where all reference to external parameters is abolished and the evolution is defined in terms of correlation between Dirac observables. First, one chooses an evolving observable as the clock. Let us call it capital T. And then one identifies the set of observables O1 until On that commute with T and describe the physical system whose evolution one wants to study. And one computes a conditional probability. The conditional probability that having observed T in certain interval, you will observe O in certain interval. This conditional probability is given as a quotient of the simultaneous probability of measuring T and Q, or O, divided by the probability of measuring T. Notice that the parameter T is associated to a variable used to define the evolving observables that, as we have discussed, is not associated with any observable quantity, but with a kinematical quantity. And we consider that this variable is an ideal and observable quantity, and due to that, one integrates over all their possible values of T. We have shown that this definition leads to the correct propagator plus quantum corrections, but the Schrödinger evolution is modified. There is a crucial difference with the standard evolution that can only be neglected if one uses an ideal clock where T and capital T are perfectly correlated quantities. If this is not the case, the Schrödinger evolution is modified, and you have an evolution where you have additional terms. The first two terms describe the evolution of the density matrix when they obey a Schrödinger equation, but you have an additional term proportional to the rate of spread of the wave function of the clock. Recall that we are considering quantum clocks, that is, clocks as an atomic clock. The evolution is given by a master equation of the Lindblad type, and pure states evolve into mixed states. The use of physical clocks required by a quantum gravitational description of time induce a fundamental loss of unitarity unless it is possible to define a perfect clock. This loss of coherence has been observed, for instance, in radio oscillations. People have conjectured that there are limitations in clock precision in a quantum gravitational system. As we do not have a complete theory of quantum gravity, this is a contentious issue. Phenomenological arguments have been given by Saleker and Wigner, Yu, Karoliassi, Lloyd, Frenkel, leading to similar limitations based on two main effects: quantum fluctuations and black hole formation. We have recently given a simple argument leading to a fundamental minimum uncertainty in the determination of time intervals consistent with the previous estimation. It only relies in the uncertainty in principle between time and energy and in time dilation in a gravitational field. And the result is the following: the uncertainty in the measurement of a time interval is always greater than the power 1/3 of the time interval we are measuring times the power 2/3 of the Planck time, and something similar with the length. This, when the quality holds, then you have the best accuracy than one can get. And with this accuracy, the solution of the master equation I have shown in the previous slide takes this form. The first two factors correspond to the standard evolution, but there is a correction, which is a damping factor proportional to the power 2/3 of the interval and the square of the Bohr frequencies. And therefore, the density matrix decoheres and tend to take a diagonal form. And pure states evolve into statistical mixtures, and the out-of-diagonal terms of the density matrix asymptotically vanish, and the system will present a fundamental loss of coherence due to this effect. These effects, together with the standard environmental decoherence, allow solving the problem of measurement. I have to say that this is a very small corrections between because of this power of 4/3 of the Planck time. Let us recall what is the standard scenario of environmental decoherence. A quantum system interacting with an environment with many degrees of freedom will give the appearance that the initial quantum coherence of the system is lost. For instance, for a two-level measuring device, let us assume that the density matrix of the device initially is in a pure state, psi. With this state is equal to a linear combination of the two basis elements in the two-dimensional space. After interacting with the environment, the reduced density matrix of the device takes the form given here, which is quasi-diagonal. The first two terms correspond to the diagonal terms, and the last two terms correspond to the coherences. And here appears a factor Z that is the product of oscillatory terms with different frequencies corresponding to the different couplings of the measuring device with the environment. This factor vanishes after a decoherence time because the cancellation of the different oscillatory terms. And the measuring device takes an almost diagonal form. This is usually interpreted in the sense that then one gets for the measuring device something that is very similar to what one obtained after a measurement. But the problem is that the measuring device is still coupled with the environment. And the interference terms are still present in the environment. The total system is still in a pure state after the coherence, and coherence can be, in principle, be revealed by measuring a suitable observable of the total system, including the environment. A second problem is revivals are present in closed systems according to Poincaré's recurrence theorem. After a very long time, the off-diagonal terms become large again. and the out-of-diagonal terms of the density matrix will recover the initial value. This is called the problem of revivals or recurrence of coherence or recoherence. Both problems are solved by the combined effect of the fundamental decoherence induced by real clocks and the fundamental bounce induced by quantum and gravitational effects to the measurement of time intervals and distances. Due to the fundamental decoherence induced by quantum clocks, the expectation value of the observables of the complete system, including the measuring device, and the environment differ from one obtained when an event occurs by an exponentially vanishing quantity. A similar analysis allows to show that revivals are also prevented by the modified evolution. When the multiperiodic function in the coherence tend to take again the original value, the exponential decay due to the evolution with real clocks, given by this last factor, completely hides the revival under the noise amplitude. Finally, the previously mentioned fundamental bounds in space and time measurements prevent distinguishing between exponentially small differences. When the fundamental bounds for measurement of time intervals and distances are taken into account, the final state of the measuring device coupled to the environment rigorously coincides with an exact statistical mixture. In other words, the final state represents a set of possible outcomes with their corresponding probabilities. If an event occurs in statistical mixtures, the conditional probabilistic predictions about the future behavior of the system are not perturbed by the production of the event, and the evolution is always described by the same master equation. We have shown that in a quantum gravitational universe, the states evolve into statistical mixtures, and therefore it is possible to explain why events take place in measurement devices without any violation of the equations of motion. We don't need to consider two different types of evolution as in the standard formulation. Notice that the previous analysis tells us when events may occur. It does not provide an explicit mechanism for the selection of one of the possible outcomes. Our point of view about this problem is that when the state of a system takes the form of a statistical mixture, events occur. This statement could be considered as an ontological postulate, being the role of physics to predict when the events can occur and with which probability they occur. The Montevideo interpretation determines the condition that a quantum system should satisfy for random choice to occur, leading to instantiation of new events, represented by projectors in the Hilbert space and their probability. It explains how and when a definite reality appears at the macroscopic level. This criterion transcends the measurement process and applies to the production of events in a macro system. It is completely objective and do not require the intervention of any observer. I will conclude with some philosophical considerations. If the fundamental nature of the world is quantum mechanical, and we adopt an interpretation that provides a criterion for the occurrence of events, we are led to an ontology of objects and events. Based on this ontology, objects, I'm speaking about atoms, crystals, or cells, and events can be considered the building blocks of reality. Objects will be represented in the quantum formalism by systems in certain states. An object is characterized by its disposition to produce events in certain environment. For instance, to produce a click in a Geiger counter. At the beginning of the 20th century, it was observed that an ontology of events allow us to face the problem of consciousness in a promising way. The philosophical current called neutral monism basically maintains that events can be associated with physical aspects as well as phenomenal aspects like feelings or sensations. The physical aspects result when we access to them from the outside, as we do in our laboratories. the phenomenal aspect would result from the first-person access, like the one we would have in our brains. The sensations would then be a particular class of events to which we have direct access. Throughout his life, Bertrand Russell adopted different positions close to neutral monism. For instance, in 1927, he said, matter in a given place are all the events that are there. And he goes on to say that such vision of matter implies that we do not have to deal anymore with what used to be mysterious about the causal theory of perception. I think that an ultimate scientific account of what goes on in the world will resemble psychology rather than physics. I think that if our scientific knowledge were adequate to the task, it would state the causal laws of the world in terms of particular events, not in terms of matter. Causal laws so stated would, I believe, be applicable to psychology and physics equally. Can quantum mechanics help to understand the problem of consciousness? Briefly, there exist three reasons for considering that quantum mechanics may help to explain conscious phenomena. Randomness, that is the fundamental role of the production of events, in the production of events, have free and cause choices of the system, may help to explain the effectiveness of our mind in the determination of our actions. Ontology, the nature of the fundamental objects of the quantum theory that is more neutral towards the dichotomy between the material and the mental. And coherence and entanglement, the non-local properties like entanglement of the quantum state that give rise to top-down causation and could contribute to solve one of the central aspects of the hard problem of consciousness that consists in explaining the unified and componentless way in which conscious phenomena appear to us. However, it is not clear how quantum mechanics would contribute to understand consciousness in a biological environment where the coherence occurs very quickly, like our brain. In fact, it is usually believed that in a biological system, the coherence would destroy long-range quantum effects. This was shown, for instance, by Max Tegmark in the year 2000. However, during the last decades, several biological processes where quantum mechanics plays a crucial role have been discovered. Photosynthesis, spin-dependent magnetic sensibility, the avian compass, DNA mutations, fluorescent proteins, ion channels. All these processes are discussed in the nice book by McFadden and Al-Khalili, Life on the Edge. And in the year 2015, a model for quantum consciousness was proposed by Fisher. It is based in a mechanism for entangled macroscopic microsystems protected from the coherence effects based on the nuclear spins of the phosphorus belonging to Posner molecules that have this form. This molecule can protect the qubits of the phosphorus nuclei from the coherence on very long times, allowing the formation of entangled systems of many particles and thereby serving as a working quantum memory capable of interacting with a neural system. Effects on the nuclear spins on the behavior were first observed in lithium isotopes. There, it is well known that lithium have properties on the psyches of human beings and other animals, and different isotopes have different effects, and they have exactly the same chemical properties, and the difference only lies in the nucleus. And this led Fisher to this idea We have discussed that in a recent paper. An empirical verification of the existence of quantum processes in our brain would allow to put the issue of consciousness on empirical basis. I conclude mentioning a couple of works, one paper and a book. Thank you very much. I don't know.
Thank you, Rodolfo, for your talk. If somebody have a question or comment, please say. Olympia Lombardo.
Thank you, Rodolfo, for the interesting talk about time. It's something very interesting, always very interesting. I want to know if I understood rightly or not, how do you construct the time operator? You construct the time operator, yes, it's very at the very beginning, yes. Because then everything runs very well. But yes, first that one. So that one is a function of small t. That small t cannot be a parameter, external parameter. It needs to be a variable, some variable that is not observable.
Right.
My question is, in what sense, I mean, in what extent this can be compatible with the relational construction of Page and Waters or of Rovelli? Because they are taking this idea of defining a small t relationally like a variable,
yes,
any variable. I mean, and this is a step further. You define an operator,
yes,
big T. I mean, but this can be made compatible with that kind of constructions, or there is something very, I mean, different from the very essence.
No, there is something very different. The T may be any variable. You may consider, for instance, you may describe the evolution of a particle using another particle as your clock, the position of another particle as a clock. In this case, the capital T will be the position of the second particle.
Mm.
And T would be this unobservable parameter. It is important to choose the small t in such a way that the evolution is is constant. The rate of evolution is constant. This is always possible to do, and this was the basis of the solution proposed by Hen and the other people to the original proposal by Page and Waters. Because the proposal by Page and Waters, in fact, doesn't work because they don't get the correct propagators. But it is possible to make sense of this proposal using kinematical variables, and this was done very recently, the last year, by these Austrian people. But here, I'm defining the conditional probabilities by this expression, where I consider the quotient between the simultaneous probability and the probability of measuring time. But the main difference is that I don't know what is the value of the ideal unobservable parameter small t. And then I need to integrate over all possible values. As t is chosen in such a way that the evolution has a constant rate, then the integration measure is simply 1, and the definition works perfectly, and this is the exact result. We have proved that with this proposal, you recover the standard propagator between 2 points for a particle being in time t1 at certain position and then at time t2 in a different position. you obtain the quantum mechanical propagator plus quantum correction, and these quantum corrections are related with this additional term in the master equation.
Okay, thank you.
Pauli, do you have a question? Or?
If there is time, yes. Do I have time?
We have some minutes.
Okay, yes. I'll try to be quick. If I understood correctly, in this ontology, you have objects that can generate events. So if I understood correctly, these are essentially probabilistic. This is an essentially probabilistic interpretation, and there are no hidden variables. If that's correct, I would like to know what you think about the fact that there are some people that say that if you have a cosmological solution, like a classical solution to the Einstein equations, you can look at the universe from the outside and everything is fixed. So you don't have a place there to a non-deterministic or fundamentally probabilistic behavior. So I would like to hear what's your take on that, and if I make sense of what I'm saying.
As I mentioned here, what we have is that the evolution of the total system, including the environment, ends up being in a statistical mixture. And we assume that when the system takes this form, then one of the elements of this mixture is instantiated in an analogous way of what happens in the modal interpretation. But here, only when the state takes this form, because when the state takes this form, they are statistical mixtures, nothing modifies the evolution. You may always compute the conditional probabilities and the results are the same before and after the occurrence of the events. Simply, you actualize the information if you observe one of the possible outcomes of the system.
Okay, I see. Thanks.
Okay.
I have a little question. Do you need a special condition or like intense gravity or something to that this equation give a significant non-unitary effects? Or
this equation depends on the rate of spread of the wave function of the clock. All the clocks we have a rate of spread, but the question is if there is a fundamental bound, and quantum gravity suggests that these bounds exist, and that was what I discussed with these inequalities. And then I use these inequalities in order to compute or determine if a quantum system, a quantum measurement device is possible to have an evolution that ends up in a statistical mixture for the measuring device. And the answer is positive with this bound.
okay, thank you. Well, if there is no another question, we thanks to Rodolfo for your talk. And the next talk in charge of Thomas Friedman, but I don't know if he is connected.
Okay, thank you.
Thank you.
Thomas said that he had another appointment, but he will try to connect in point just a few minutes before. I think that we should wait a little bit to
Okay,
check.
we can make a little break, a coffee break of 5 minutes.
Yeah, perhaps 5 minutes. Yeah. Thomas, sorry. Are you there? Yes. Thomas, please try to unmute your phone and your camera so we know you're here.
Yep.
Great. Okay. If you want, sorry for if the instructions were not clear. So now you can hear us, right?
Yes, I can.
Great to have you here. Please try to share your screen if you can, so we can check whether it works or not.
Let's wait a minute. So
Now we are sharing already. So if you just go to the PDF or the PowerPoint file and you open it, it will be
Yes.
just fine.
Yes.
Yeah. Great.
Is that working?
Yes. Perhaps you can try full screen or something like that, or presentation mode. Or...
Sorry. It's so ridiculous.
Somehow the browser interposes between the presentation and the screen. I don't know why.
Let's see if the full screen does it.
No. The full screen on the presentation. You should go. You should go to the PDF or the PowerPoint file, because now we're watching at your screen. Anything you do on your screen, we can see it. But then what you have to do?
Oh, sorry. Wait a minute.
Yeah. Just minimize that the browser. Minimize it, and just go like as if you were in your computer, like putting full screen PDF, just a PDF file.
Yeah.
The minimize should be. I don't know, where is it?
Exit full screen.
Exit full screen. Yeah.
It doesn't seem there.
ESC.
All right.
Otherwise, the ESC on your computer, there's an ESC button on the keyboard. Sometimes that works. Yeah. Now you minimize that, not close, just minimize. And then you go there. Yeah, slideshow. Perfect. Now it's working perfectly.
Yes.
Thanks.
So sorry. I'm sorry for the delay. Can you see me?
Yes, we can see
You,
that.
not you.
Because I do not see you. I just see my slides at the moment. Well, maybe I'll begin this way.
Yeah, it's fine. Yeah.
All right. So thank you very much for the invitation. I'm sorry about the little contretemps of getting connected here. There's always some problem with the Stanford Zoom and other Zooms, and there was some interface thing I was not dealing with properly. But anyway, this is a talk about Cubism. I assume you all know what Cubism is, and I call it realism about what, for reasons that I hope you'll see in a minute. So let's begin. And essentially, if you take nothing else away from the talk, we can begin just by remembering this one slide where we have Bohr and Wheeler and Chris Fuchs. And the quote from Fuchs says, the accumulating ingredients for what ultimately became Cubism all originated in one form or another through Wheeler, and Wheeler through Bohr. And so in trying to answer the question, what is Cubism realism about? I'm going to follow this trajectory through Bohr and Wheeler and see if that actually makes sense. I think it does make some sense, although I think there are many unanswered questions about it. I think it's a tremendously interesting program to think about philosophically. And by the way, please interrupt me at any time if you have questions, comments, criticisms, whatever. So this is what I'm going to try to do in the time that I have. I'm going to start with 5 Cubist themes. I'm going to try to tell you what realism is not. I'll try to tell you how the Cubists view their own realist doctrine and how more traditional realisms fight back against Cubism. I'm going to look at the notion of physical reality through the lens initially of E.T. Jaynes and applying that lens to Bohr and Einstein. I'm going to talk about Wheeler's Bohr, and I'm going to conclude with just a brief remark about from Wheeler to Chris Fuchs. Here are the 5 themes for Cubism. All of quantum theory is first person for the person using it. I assume everyone knows that. I assume everyone knows that Cubism has a radically personalist view of probabilities, so that probabilities and thus the quantum state are not directly descriptive of the quantum world, but represent an agent's degrees of belief concerning future experiences. That quantum measurement outcomes just are personal experiences for the agent gambling upon them. And gambling, of course, is here something done in accordance with Born's rule, a normative rule, according to Cubism. Cubism is not an instrumentalism, nor is it a non-realism, but proposes a new kind of ontology or metaphysics, a participatory realism, according to Fuchs. And it's not a solipsism. The agent, after all, is going to respond to experience, structuring beliefs in accordance with the quantum theory. And let's begin with what realism is not. This gentleman, Bernard Williams, was briefly my colleague at Berkeley. He shared his time between Berkeley and Oxford, Bernard Williams. And in a very perceptive review of a book by Hilary Putnam back in the 1990s, Bernard Williams told us at least what he thought realism was. I'm not going to follow him the whole way, but I'm going to spring off of what he set up. Realism, he says, is the idea that we live in a world that exists independently of us and our thoughts. So what is this idea of realism that this side of insanity we all share? And I want to work on this side of insanity, not the insane side. Well, the insane side is a metaphysical realism. It's the view that we can conceive of the world in some way quite independent of our own theories and the terms in which we describe the world, and that we can sensibly inquire whether our descriptions correspond to the way the world really is, the way it was before we got to it. And so the presupposition of metaphysical realism is that somehow, because we can sensibly inquire, we can ascertain whether our descriptions accurately fit the world. But of course, the world does not describe itself. It's impossible to directly compare our descriptions to a mind-independent reality. And so what are we to make of the idea of truth as a correspondence of our beliefs or descriptions or representations or theories with the way the world really is, since we cannot directly compare our descriptions to a mind-independent reality, to a world that doesn't describe itself? And so without metaphysical realism, which I would put on the other side of the insanity divide, what is the meaningful idea of realism under dispute? One possibility, of course, is a scientific realism that allows for the possibility, according to Stathis, of a divergence between what there is in the world and what is issued as existing by a suitable set of conceptualizations and epistemic conditions. I'm not going to follow that possibility because, as I've just tried to tell you, I can't make sense, and I think a lot of other people share this view, of any kind of notion of correspondence between descriptions or representations and the way the world really is. Another possibility, and I'm not saying this is an exhaustive list at all, is what Fuchs calls cubism as an example of a variety of realism far too often left out of philosophy of science discussions. So now let's look at Cubist realism and the way the traditional realists have fought back. Well, Cubism combines these seemingly orthogonal philosophical views, the epistemic primacy of first-person experience, all the way down, so that quantum theory is essentially a user's manual for dealing with quantum experience, that is, observations and measurements. And realism, in the first sense, is that of attempting to make statements about how the world is, what the stuff of the world is, according to Fuchs in various statements. Cubism is going to try to bundle 1 and 2 together into a view that Fuchs has called participatory realism. And I'll try to give you a brief account of what that is from its genesis through John Wheeler and Niels Bohr. Well, what is Cubist realist about? Well, for one thing, or two things, the Born rule and the Schrödinger equation. These are not mind-independent laws, as realism 0, that would be metaphysical realism, but normative structural rules. These are realistic statements because the normative, the should follow upon the factual is. Since these are rules or equations for tracking some features of reality. That is to say, the Born rule or the Schrödinger equation are statements, quoting Fuchs, striving to be statements about reality independent of a particular agent. Striving to be, not as statements about a reality independent of a particular agent. There's a difference there. One has to do with aim, one has to do with actuality. And Cubists are realists about the various structural theorems of quantum mechanics, these no-go results, whose collective message, according to Cubism, is that pre-established values of physical quantities do not exist, but, as they say, using Heisenberg, measurement makes its answer on the fly. Now, the realist critics, including Harvey Brown and Chris Timpson, John Ehrman, Matthew Pusey, et cetera, are unable to locate Cubism on the customary spectrum of possible realist views of physical theory. And so they tar Cubism with either an instrumentalist or an anti-realist or even a solipsistic brush. And here's a quote from Harvey from a paper in 2017. Cubism, in the words of David Merman, a convert to Cubism, maintains that scientific pictures of the world rest on the private experiences of individual scientists, and each of us has a view of the world that rests entirely on our private personal experience. Harvey's gloss on this is that it seems that the basis of a variant of Berkeleyan idealism suffuses Cubism, which Harvey says is admittedly a provocative claim. Well, indeed it is. To try to get through the fog of what Cubism might mean by realism, I'm going to start with E.T. Jaynes, because Fuchs often quotes E.T. James's metaphor that Bohr and Copenhagen had scrambled together the objective and subjective parts of quantum theory into an omelet. And so to the foundational worker and to the philosopher, there's a primary need to unscramble the omelet to separate the objective and the subjective factors. And Jaynes comments on this, that far too much of the controversy over realism fails to see that both concepts, reality and knowledge of reality, both are essential to scientific practice when it matters. but it's also essential to distinguish them. And this problem is massively compounded when the term physical reality is used in both this ontological and epistemological sense to mean very different things. So what about Bohr on physical reality? According to Bohr, as many of you know, an objective account of physical experience is to include both experimental arrangements and the results of observations under these conditions are to be expressed in unambiguous language with suitable application of the terminology of classical physics, quoting chapter and verse. And then in a very interesting postscriptum to this discussions with Einstein paper that was never published, it was supposed to be published in a reprint of that discussions with Einstein's paper. In the volume, I think it's called Quantum Theory and, well, I've forgotten the title of the volume, but it came out in the 50s, late 50s. But in this postscriptum, Bohr writes that the proper meaning of the words physical reality must refer to the content of an objective account of physical experience. And what is an objective account of physical experience? It's that both experimental arrangements and results of observations under these conditions are expressed in unambiguous language with suitable application, blah, blah, blah. So for Bohr, closed systems, undisturbed systems, systems that are not observed, are real, but they escape the objective description that gives meaning to the term physical reality. That's a crucial distinction. That's the distinction that E.T. Jaynes was pointing to. What about Einstein? Well, I think that we can say, as we will see in a minute, that Bohr was in many ways sharpening his philosophical tools against the grind of Einstein. And Einstein is also important for the views of Chris Fuchs. In a passage from On Participatory Realism, Fuchs says, here's the way I view my own realism. It can be taken straight from the playbook of Albert Einstein. And here, there's a long quote. Some of you may be familiar with this quote from Einstein's reply to criticisms in the Schmidt volume. I don't need to read it all here. I will just start about halfway down, where it says the above mentioned objective factor, and Einstein's talking about the need to separate the subjective perceptions from the objective factor of concepts. The above mentioned objective factor is the totality of such concepts and conceptual relations as are thought of as independent of experience, of perceptions. So long as we move within the thus programmatically fixed sphere of thought, we are thinking physically, insofar as physical thinking justifies itself by its ability to grasp experiences intellectually, we regard it as knowledge of the real. After what has been said, the real in physics is to be taken as a type of program to which, however, we are not forced to cling a priori. So here Einstein is distinguishing the real from knowledge of the real. Knowledge of the real is what is grasped by the conceptual organization of our perceptions. Let's turn to John Wheeler's Niels Bohr. And of course, Wheeler is known for the mantra, no elementary phenomena is a phenomenon until it is a registered phenomenon. Wheeler comments on this that the notion of phenomena was introduced by Bohr to meet and overcome the objections of Einstein. And indeed, in the knowledge of the real, for Bohr, that's going to be the knowledge of what is given to us as phenomenon. And Bohr says this, reserving the word phenomena solely for reference to unambiguously communicable information, in the account of which the word measurement is used in its plain meaning of standardized comparison. That's from a paper of 1959. So for Wheeler, an elementary phenomenon, as you probably remember, is an answer to a yes-no question posed in the situation of quantum measurement. And Wheeler thought that just one of the lessons of Bohr was that quantum states are information, according to Fuchs. For Wheeler's Bohr, you can symbolize the role of observation in the very definition of reality. And here you see the iron posts of observation defining the big capital R, which is reality. Wheeler says in a paper from 1977, he says this in many other places, the results of observations and experiments regarding what we can communicate to others in plain language, what we have done and what we have learned, quoting Bohr, serve as the iron posts of reality. All else is papier-mâché, plastered in between them. And so here you see reality with the iron posts of observation papered in between with essentially imagination and theory. This famous diagram is a symbolic representation of the universe as a self-excited circuit or system brought into being by self-reference. This is an image that many people think drove Wheeler over the edge of sanity into complete solipsism. I think that's wrong. I think all he's doing is trying to gloss Niels Bohr. What Wheeler says is no consciousness, no communicating community to establish meaning, then no world. And here we have essentially the equivalence of the notion of world and physical reality. Physical reality or world is that part of reality invested with meaning or information. Oh, of course, this raises the question of what did Wheeler mean by meaning? And here Wheeler turned to a quote from a paper of Dagfinn Folsdal of the University of Oslo from 1974. But Dagfinn was also my colleague here at Stanford for many years. He's now emeritus, where Dagfinn says that meaning is the joint product of all the evidence that is available to those who communicate. So if you think about evidence and observation and communicate and unambiguous communication in the language of Niels Bohr as language that refers to what we observe and tell people what we do when we make experiments and communicate that in the language that includes classical physics, that's what we mean by meaning. And Wheeler, interestingly enough, I've counted by my count at least 7 papers in which this passage is repeated. This quote from Folsdal that meaning is the joint product of all the evidence that is available to those who communicate. For Wheeler, what we call reality, that vision of the universe that is so vivid in our minds, we plaster in between a few iron posts of observation by an elaborate labor of imagination and theory. So again, I want to insist on this equivalence of reality and physical reality. Physical reality is just that part of reality invested with meaning by observation, imagination, and theory. And I think you will see the resonance of that with the term physical reality as used by both Bohr and by Einstein. This is my last slide, so there'll be time, hopefully, for criticisms and comments. From Wheeler to Fuchs. This is a passage from On Participatory Realism. One thing that is absolutely clear in Wheeler's writings is that the last thing he was pursuing was an instrumentalist understanding of quantum theory. He thought that quantum theory was the deepest statement on nature and reality ever discovered by physics. Thus, he would play little dialogues with himself, like this one. The strange necessity of the quantum, as we see it everywhere, should have a way to come into being. If true, and it is attractive, it should provide someday a means to derive quantum mechanics from the requirement that the universe must have a way to come into being. Now, I think that if you look at the history of where Wheeler was talking about this, in the 70s and 80s, he's very much influenced by discussions coming out of Cambridge about the Anthropic Principle. The idea that we can only explain what we observe in the initial conditions giving rise to the cosmic microwave background. We can only explain such initial conditions by some sort of anthropic process or some sort of anthropic postulate, because otherwise those initial conditions are so unbelievably rare that we would have to basically just say that it was an inexplicable coincidence. So this notion that I think that is guiding participatory realism is a Wheelerian notion. It has these Bohrian antecedents. I think it has also some part of an antecedent in Einstein's notion of physical reality, that the universe comes into being as that part of reality invested with meaning or information. And of course, for Wheeler, that information was just the answers to yes and no questions. So with that, I will stop, and let's see if I can put you. Let's stop that and go back. Yeah.
Thank you for your talk. If somebody have some question or comments, please say it. No?
Well, I think that, yeah, but Olympia also is asking, I think, but she's sending, I don't know if for everyone. Yeah, okay. But I was also trying to
First you.
make a question. Yeah.
Yes, we were. First
I don't
you.
know. Yeah.
Hi, Olympia.
There is a question from Christian Lopez too. First,
Yo creo que está primero Federico, first Federico, then me, and then Christian. And we were.
Yeah, but because somehow I don't know why we were just putting cues between Olympia and me, as it was really ridiculous. No, mine was just a simple observation or question, which is, what do you think about this? When Chris Fuchs said, I don't know, a couple of years ago in Baku that the Cubism interpretation was about some form of realism, I was really astonished. I couldn't believe it. But my impression, I think I understand where he wants to go. But my impression is that you could replace Cubism, but some more elaborated philosophical tradition like phenomenology or something like that. And you could just erase all of that and just read the right books in philosophy, and you will obtain something much more elaborated and interesting with its own problems, of course. But what will be your take on that observation?
Well, of course, that's what people like Michel Bitbol and Harold Wiltje and other people are trying to do just now. And I think there's much merit in that. I think that one can understand Cubism in a parallel way. And I don't think that's in any way antagonistic to phenomenological interpretations of Cubism. But I think it's deeply rooted in a tradition in physical theory. It actually goes back, I think, to Heinrich Hertz and Boltzmann, but it's certainly present in Einstein, I think, and in Bohr, in dialogue with Einstein and in opposition to Einstein, where we recover this notion of physical reality as what we can say about the world, what we can communicate about the world, what we symbolize the world, our descriptions, our representations, and everything else. And that's a perfectly good notion of realism. Does it actually correspond to the way the world really is? Well, then we can say, well, that question doesn't really make any sense. And I think that's how the realism controversy should be ended. So yes, it's very puzzling to call it a realism, but certainly for Einstein, and I think even for Bohr. I mean, Bohr says somewhere that the question about the reality of the external world is simply not interesting. It's something that philosophers think about, but it's just totally obvious. Of course, the external world is real.
Thanks.
So Yes, so thank you, Thomas. This is very interesting because the question of realism in quantum mechanics is very basic. My sense is that, well, I mean, I agree, absolutely agree that reality cannot be described from the God eyes viewpoint. So you access reality from a conceptual scheme, and that conceptual scheme is embodied in your language. So your description, and this is realism. I mean, I'm not saying that this is not realism, because you accept that there is a reality there outside your language. But my sense, my questions here is why they accept, I mean, this Cubism and Bohr even, assume that the conceptual scheme must be always classical. I mean, measurement, information, communication, in this language in which we communicate is a classical language. Why not thinking that we have to change our conceptual scheme or we may change our conceptual scheme to access reality? Not even, and even more, that we can have different conceptual schemes to access to the same reality and to obtain different accounts. I mean, if physics places iron posts and we complete the figure, the picture, I mean, there are many pictures that we can make with the same iron posts. So I don't understand why. I mean, I'm not saying that Cubism is not acceptable. I don't understand why they consider that this is the right way. If you accept that we access reality from our schemes, why this is the right way to access reality?
I think the answer, insofar as Cubism can answer this, is going to be drawn from Bohr. And I think that for Bohr, so why the insistence on classical language? It's because of what he means by unambiguous communication. If we have different conceptual schemes, we don't communicate. And the thing is, why is unambiguous communication so important? It's because that's how objectivity is defined, when we can communicate what we have done in the lab and what we have drawn from that. And if classical language is, for Bohr, essential to that, it's very much like the idea that, in some sense, all of our evidence of the outside world has got to be, the outside world is everything impinging on our sensory apparatus, has got to be expressed in terms of what Husserl called the natural attitude, the language of everyday life. It's very similar in its relation to that. And for Bohr, the concepts of classical mechanics were very close to the concepts of everyday life. And of course, he showed that they have to be restricted in their application to quantum mechanics. So basically, my answer to you, Olivia, is simply that we have this notion of unambiguous communication, which fuels the notion of objectivity. And the unambiguous communication is, for Bohr, rooted in the ordinary language that we use, supplemented with the language of classical mechanics.
Okay. Oh, thank you.
Christian Lopez.
Okay, thank you very much, Thomas, for the talk. It was really interesting. My first question was quite related to Federico, so I now have to change it. So let me take something that you said in your reply to Olympia, when you said that there is some sense in Cubism that refers to objectivity. And now I was wondering if any notion of objectivity is not in tension with taking too seriously the idea of first-person experiences. I mean, if I got you right, You said that for Cubism, one of the main tenets is that, well, the first person experience plays a crucial role in our understanding of the world. But how can I guarantee that different persons having different first person experiences can correlate their experience in some way that we can recover some idea of objectivity? I'm thinking, I mean, in some sense, this looks like the Leibnizian world in which we have the monads with their own representation. But to guarantee that they are having the same representation, you need an additional principle that correlate. And so my question is, there is something like that in Cubism that guarantee the...
Well, actually, that's a really good question. And it goes to a very deep and interesting problem. If you are, for example, really honest as an epistemologist, you're going to have to admit something like the idea that it's my experience that is the most primitive experience that I have of the world. I mean, everything that I know is ultimately, what impinges on my sensory apparatus, right? And you can call this position solipsism. I think methodological solipsism is probably a better word for it. It's the position that Carnap introduced in the Aufbau, but followed Russell and various other people who simply started from the notion of sense data. That was the primitive, rock bottom, ground level epistemological bedrock. Now, where do we get objectivity? Where do we get intersubjectivity? This comes through language. It comes through the fact that individuals, scientists, are members of a linguistic community. They're not to be abstracted from that specialized situation. And by sharing that language, they are part of a community. They can communicate with one another. And the question of, therefore, of the constitution of intersubjectivity from this methodological solipsism really has to begin with the notion of a shared language, a shared community, shared experiences. Many of the things that Kuhn would talk about as a paradigm, what is common to individuals of a particular area of inquiry, something like that. So I think that's right. I think that Husserl in his phenomenology actually makes that move himself because he is a radical first-person idea epistemologist, that phenomena are individual to people first and foremost, but the constitution of intersubjectivity comes through shared experience and shared language. A shared experience, of course, is experience that is communicable in language. It's not, your experience is my experience, and we differ about the taste of pineapple or something like that, as Locke would say. No, we have a language in which we can communicate about it. And I think that notion of language, common experience, rooted in common activities and common upbringings, common training, et cetera, that is absolutely crucial for how we get out of the solipsistic paradox that, we're not Leibnizian monads.
Hey, thanks.
Olympia.
Yes, just to, now I understand better. I mean, language is a fact. I mean, it's an assumption, but not only the fact that there is a language, but that there is this language. This is the point. I mean, this kind of language. Was my point about classicality. I mean, this kind of language is something that must be taken as a fact. And well, and perhaps philosophically, we need to find an explanation why this language is in this way for everybody, and perhaps just for evolution or blah, blah. But I mean, not only, I mean, the presupposition is not only that there is a language in which we can communicate our experiences, but that language is this one we have. I mean, and that this language is the same for everybody in all cultures, all times, and it is this kind of a condition of possibility for experience.
Yes,
okay,
exactly.
This language in particular. Thank you.
No, that's exactly right, I think.
Okay, we are in time, so this was thank you, Beckman, for the talk and the people who asked questions and made the comments. This was the last talk for today. So we will continue tomorrow and at 8:30.
Okay. I'll try to tune in for some of your talks. There are 5 hours difference in time from me, so it's a little difficult, but I will try to do it. And it's so wonderful to see all of you again, Sebastian, Olympia, Federico, it's Christian. It's really nice to see you all again.
Thank you. Thank you.
Yes,
Thanks,
The
Thomas.
same.
Thanks, Thomas.
The same.
Thanks.
A lot of time we don't meet. I hope
Yeah.
that we can meet personally very soon.
I'm hoping so too. May that happen.
We will share some wines again in the
Yeah.
Yes, yes, of course. Yes, of course. At least that. Yes. Good.
Yeah.
Thank you.
Thank you.
Okay, thanks.
Bye.